Hello students, let us begin Module 13, Determinants 2. As the title suggests, this is a continuation from the previous module, so let's begin with a review. How did we define determinants? We defined it recursively starting from the simplest case, and the simplest case is the determinants of order 1, which are just real numbers, so all the rules for real number arithmetic will apply. By the way, 1x1 matrices, square matrices of order 1 are just real numbers, and so are their determinants. Okay, the next simplest case is the determinants of order 2, the simplest non-trivial case. The determinants of a 2x2 matrix ABCD is defined as AD minus BC following this crisscross rule or zigzag rule. One of more important application of it is the inverse matrix formula. And here, please note that the denominator here, AD minus BC, is nothing other than the determinant. So this whole formula is invalid when the determinant is 0. Indeed, we'll prove that any square matrix is invertible. Any square matrix for all order, not just order 2. If and only if the determinant is non-zero. We're going to prove it here in Module 13, but of course that's going to be a bit too hard at this moment, so let's continue over the review. And the next topic is the determinant of order 3, which can be defined like this, using the crisscross or zigzag rule, but preferred definition is through recursive definition, focusing upon one of the rows or columns. Here I use the first row, but I could have used some other rows or columns. Let's explain this in a little bit more detail in the next subsection when we deal with the determinants of arbitrary order. You can use the expansion with respect to an arbitrary row. Here, in this particular case, I'm using the fourth row. Focus upon the fourth row here and take the entries A41, A42, A43, A45, and so on, as you see here, and multiply the determinants of the deleted matrices, determinant of A41, determinant of A42, and so on. And finally, the signs. Always we begin with plus sign in 1 entry, and then we change sign each time I skip to the next row or next column. So here we go, plus, minus, plus, and then minus. That's why we are starting from negative here. Next, plus, minus, and so on. We have all these signs, alternating signs, because of that. That's one way to describe the determinant. And here's another. You can use columns. Here, in this case, I took the third column here, A13, A23, A33, and so on. And please look at the sign. Let's begin with plus here, 1 entry, and then minus, and then plus. So we begin with plus sign. Next, minus, plus, and all those alternating signs. That's another way. It turns out whether I use row or column, as far as the determinants computation is concerned, they are equivalent, and consequently, their properties. Here are 3 basic properties of determinants based upon the column: multilinear, linear with respect to each column while leaving all the other columns exactly the same, or alternating. If I switch 2 columns, then the determinant becomes negative, or equivalently, if I have 2 identical columns, then the determinant is 0. The proof of the equivalence is left to the students. And finally, the determinant of the identity matrix is always 1. Now, third rule, identity matrix is diagonal, so it stays identity if you switch row or column. If you take transpose, it stays the same, no problem there. But for multilinear and alternating, we can use the row and column equivalence. Here, multilinear is explained in terms of columns, and also alternating properties with respect to columns. But then again, if you go over to the formula for determinants, row or column, they're equivalent. Therefore, with respect to rows, we have to have the same properties, multilinear and alternating. Some further properties of determinant. Determinant of transpose stays the same. Yes, that's really obvious because determinant's computation is equivalent whether I use row or column. So if I switch row and column, row become column, columns become row. In other words, if I take transpose, they'll not change anything. Next property, multiplicative property. Determinant of product is the same as the product of the determinants. Now this is not easy to prove, and I'm not going to go there. Just remember the result here. Next, determinant of the inverse is reciprocal of the determinant. And this is not difficult to prove because we can use the identity property. Determinant of the identity is 1, and this property with A and A inverse, then you're going to get this one. It's not too difficult. Important part is the implication. We need determinant in the denominator. So if this is 0, then I'm not going to get A inverse, you see. And as for elementary row operations and elementary column operations, it'll turn out that if I multiply a C to entire column or row, then you're just multiplying C to entire determinant. If I switch two columns or if I switch two rows, then determinant will become negative of itself. And finally, if I multiply certain scalar to a certain column and add it to another column, or do the same thing, corresponding thing to the rows, then the determinant will remain the same. These are three elementary column operations, and determinants behaved accordingly. We got the same thing for elementary row operations as well. And that was a quick review. All right, let's go to section 1. And section 1 calls for some more reviews. And these are reviews for something we did a long time ago. Section 1, rank and determinants. Okay, good. Determinant, we learned it in module 12 and we just reviewed it. Now, what is the rank? That's something we did a long time ago. I think maybe it's module 4 or 5. I don't remember exactly. Somewhere around there. And here's a reminder. For any matrix, m by n real matrix, we can consider row vectors a1, a2, all the way over to am in subscripts. And each of those row vectors are n-dimensional vectors because there are n columns here. So the row space is a subspace of, oh, excuse me, there's a typo. Sorry about that. Rn, sorry about that. Okay. So the row space is a subspace of Rn generated by these row vectors. A1, A2, A3, all the way over to Am. And the dimension of the row space is called the row rank. So row space is a subspace of Rn because each row vector is a n-dimensional vector. So each row vector here belongs to Rn. So subspace generated by these vectors included on Rn will be, of course, a subspace of Rn. Now, what is row rank? It's the dimension of this row space. So, dimension of the subspace must be less than the dimension of the original larger space. So this dimension has to be less than n, less than or equal to n. Also, dimension is the minimal number of generators. I hope everybody remembers that. We did it a long time ago. Maybe in module 4, I think. I'm not so sure. Anyway, minimum number of generators. So this is generated by m vectors. So minimum number is going to be less than or equal to m. So here we go. This row rank is less than or equal to both m and n. So less than or equal to minimum of m and n. And are they going to be equal? Not always. Likewise, we can consider column spaces. A1, A2, A3 all the way over to AN because there are n columns. Each of this is a column, and each column vector is a m-dimensional vector. They're m rows, so there are m entries in each column. So the column space is a subspace of Rm generated by the column vectors A1, A2, A3 all the way over to AN. And the dimension of this column space is called the column rank. So this subspace has to have dimension less than or equal to the original larger space. So this dimension has to be less than or equal to m. Also, these n column vectors generated this subspace, and the dimension is the minimum number of generators. So it has to be less than or equal to n. So column rank, row rank, they're both less than or equal to minimum of m and n. And it turns out row rank and column rank are the same. And it turns out they're both same as the dimension of the image space of the linear map generated by this matrix A. Well, proof of all these can go really deep. See, as for dimension of image space, then you can recall the kernel and image and the rank theorem and those kind of things. Remember all those? They go real deep really quickly, so let's stop here. And these are related to determinants, and we're going to use those. Let's stop here, at least for now, and let's just go ahead with an example problem here. As a matter of fact, it's a little bit misplaced here. Excuse me, I think it is correctly placed. Okay, let's do this example problem first. Rank of a matrix. Find the rank of this matrix. How do you find it? We did this, let's see, well, many weeks ago. So I think some review is in order. So let's do that. And what we're going to do here is to recall that the elementary row operations and elementary column operations do not change the rank. They keep the rank the same. So starting from this original matrix A, we're going to apply a series or a sequence of elementary row or column operations. Okay, let's start from here. And first, we switch the first row and the second row, and that'll give me the second matrix. That's obvious. And the reason I did it is, of course, to get 1 in top left-hand side corner here. Alright, next. This may look a little bit unusual, and I could have removed these 3's, multiplied 3 to the first row and subtract, but somehow I decided to reduce these first row first, and what I did is subtracting the second row from the first row. By the way, subtracted the second row from the first row and put it into the first row. That's what I did. So 3 minus 2, that's 1, and then zeros do not change anything. 2 minus 1, and then 5 minus 2, and that's how I got the new first row. And the reason I did it this way is to make the next two computations easier. In order to remove these 3's, I multiplied 3 to the entire first row and then subtracted from the third row and also from the fourth row. I did these computations, and then the result is this matrix. Okay, I have 1, 0, 0, 0 here. Alright, let's start from here. And then I'm going to make this one into 0, 1, 0, 0. But then again, looks like it's going to be a bit difficult to do it with this 2 here. If I divide it by 2 and then make it into 1 and begin fraction, it'll work, but a bit of an overkilling. I don't like to have a lot of fractions. So I did elementary column operations here. I switched second column and the fourth column so that this becomes 1. Either I use elementary row operation or elementary column operation. No change for the rank, so yes, I can do that. Okay, elementary column operation I did. And then let's remove all these, and those are here. So subtract row 2 from row 1 and then put it in. That's how we removed this one and make this one 0. And then multiply 4 to second row and then add it to the third row. So that'll remove this -4 and then give me 0. And multiply 9 to the second row and add it to the fourth row. And that'll of course remove this -9 and made it into 0. And that's what this operation is. If you do it right, you're going to get that. Okay, that looks actually good. We have 1 0 0 0 set, 0 1 0 0, and here 0 0 1 already. Okay, and let's remove this too. But as a matter of fact, this last row is kind of well positioned, so that if you multiply 2 to the third row and then subtract from the fourth row, if I apply this green operation down here, then entire fourth row becomes 0. And what does that tell you? This matrix has rank of 3 or less. You see? We don't need any of those. So rank 3 or less. Okay, let's keep working. So let's take this matrix here. And we are done with elementary row operations. We use one column operations here, but we can use more elementary column operations. That is, let's remove these, -1 and +1, by multiplying +1 to the first column and adding it to the third column, and multiplying -1 to first column and adding over to the fifth column. That's how we can remove these -1s using this. Nothing changes because nothing else changes because these are all 0. Next, I can remove these 2 and 2 and multiply 2 to the first column and subtract from the fourth column, or multiply 2 to the first column and subtract it from the fifth column. That way we can remove those. And then finally, multiply these two. Remove these two. Multiply 4 to the third column and subtract it from the fourth column. Multiply 7 to the third column and subtract it from the fifth column. And that'll remove everything. And what do you have? We have this identity matrix here. And, well, that tells me that this is rank 3. As a matter of fact, you could have tell this is rank 3 from here. As a matter of fact, you could have stopped here, but these operations, the final line, are really simple operations, so I decided to complete everything and get to the identity matrix embedded in anyway. So, this matrix has rank 3. Okay, so much for the reviews, and in the next video, let's begin the real topics, the new topics of Module 13. See you soon.